Hello, so in this video we're going to look at some related rates problems. Now, one of the ways that you can kind of look at related rates is that it's really just applications of rates of change. So for example, if we consider a circle, or sorry, a sphere, and let's say that we have that the radius is r. Now we know that the volume can be given by 4/3 pi r cubed. But if I want to find dV dt, like the rate of change of the volume, it's dV dr multiplied by dr dt. But this is going to be 4 pi r squared times dr dt, which basically means that I can essentially solve for one of the two, such as like if I know that I want to know uh, when the what the rate of change is um, for the radius if the volume was changing at a rate of 200 cubic inches per minute. But then that would leave me with that I don't know what drdt is, of course. But we'll go ahead and say that r is going to be 4 inches. So what this means is that basically you could solve potentially for the drdt, because you have that would be 200 is equal to 4 pi multiplied by 2 squared drdt. Now this is going to be 4. Okay, so that's going to be 4 times 4, which is 16. So we have 200 divided by 16 pi is equal to drdt. So essentially we already know like what the radius is increasing by, because we already have that. And if you want, you can change that into 25. Okay, so yeah, you can change this into like 25 over pi, over 2 pi, sorry. And that's drdt. Now, right now, I won't even go through the process of finding, the approximation, but I will just say that, that's 25 over 2 pi, but that's inches per minute. Okay, now, in most cases, you always want to look for a diagram as needed for related rates problems. So even if it's for something as simple as like a diagram or a problem which can be modeled after a right triangle. So like for instance, if you have a car goes north and then you have that a car goes east, and then you have that there's the distance between them both. Well, you always have to find an equation that relates them both. So you have x squared plus y squared equals to z squared, which in this case, like if you want to know, like for example, like the distance between them both, then you would just find the derivative with respect to time. So that's dx, 2x dx dt plus 2y dy dt is equal to 2z dz dt. And essentially what you'll get is the following: that the rate of change with respect to the hypotenuse is going to be x plus y divided by, not x plus y, but yeah, x multiplied by dx dt plus y dy dt, and this is all divided by z. But note that z is the square root of x squared plus y squared. Okay, so what this means is that all that you would need to do is just plug in whatever the distance for x is, the distance for y is, and then substitute whatever z is. So that's not too bad, especially like if the model happens to be a right triangle. Now, one of the most classic problems that you may have is such as like if you have like a lamp and then you have that there's a man that's standing from the lamp. So like let's say like for example that you have that this right here. Actually, let's do this. Let's go ahead and just draw a line to represent the man's height. Okay, so we have that um, this man is about 6 feet tall. The distance that he stands from a light pole is 8 feet, and then the distance between him and his shadow that's casted is 10 feet. Now, the height of, let's say, like the lamp pole, it's 10.8 feet. Now, this question may say something like, okay, what if you were to label this as X and this as Y, and they tell you that the person is moving at a rate of 8 feet per minute, or not 8 feet per minute, 50 feet per minute, then in this case they might ask for dy dt. Okay, now the way of which that you would try to solve this is that you would just have to say that, well, I know that 10.8 is to x plus y as 6 is to y. Now from here you would have to basically just cross multiply and end up with 10.8y is equal to 6 times x plus y. Then furthermore, you would end up solving for y. So you have 10.8y equals to 6x plus 6y, and that equals to 4.8y equals to 6x. Now, what this is telling me is that if I solve for y, I end up with 5/4 times x. Now, that's actually just telling me like what's the ratio of like the distance from the base of the pole and their casted shadow. Okay, so if we could figure out that ratio, then that's it. In this case, we'll go ahead and say that if we differentiate with respect to time, though, we have that dy dt is equal to 5/4 times dx dt. Now, fortunately, we already know what dx dt is. It's 50. So we have 5/4 multiplied by 50 equals to, let's see, that should be 62.5 feet per minute. So we have that the shadow is moving at this rate. Now, interestingly enough, if the question asks for like, let's say like the tip of the shadow, then basically you're just going to add x dx dt and dy dt. So you would say that if z is equal to x plus y, then that means that dz dt is equal to dx dt plus dy dt. But that's equal to 112.5 feet per minute. Now, the one thing that I kind of like about these examples is that it doesn't matter how far away the person actually is from the base of the pole, because like they might ask like after the man is like 25 feet away from the pole, um, or even like less perhaps. So in some cases, like we don't even need actually to know like how far away is the person. Mostly because the logic is that the rates will never change. That if we just assume that the rates are actually just constant, that it'll just stay the same. Okay, so the main thing that you should take away from related rates is that you always want to draw a picture, find an equation, and then differentiate that equation, and then just substitute the given values so that you can find the unknown value or whatever you're trying to look for. One another equation or another problem that you might actually look at is like, for example, like a cone. Like if you have that there is a cone, basically you would just have to use like whatever the formula for the perhaps like the volume of a cone is. Um, it should be like 1/3 pi r squared times h. So like usually whenever you deal with problems that have a cone, you have to consider the cross section. So like if you have this is the cross section of the cone, then you know that this is the height or the depth of the cone, and this is the radius. So essentially, they'll kind of tell you like the radius of the cone, and then they'll tell you the height. So if you know that the radius of the cone is like 4 inches, and then if you know that the height of it is 10 inches, then that means that technically you know that the proportions is r is to h as 4 is to 10. The reason that you need this is because you might need to find the change in the volume with respect to either the radius or the height, depending. So from here, you would actually just use this equation. Um, it is possible that you could probably um, use product rule. Like if you know that the height is changing and also the radius is changing, that you can actually just use product rule to figure out what the rate of change of the volume happens to be. But I think that it should balance out in either case, like whether you substitute or not. So like this is a classic problem, which if I wanted to rewrite it in terms of h, then I would just say that r is equal to 2/5 times h, and I would plug this back into here, which that would give me that the volume is 1/3 pi multiplied by 2/5 h squared multiplied by h, and this would be 1/3 pi 4 over 25 and then h cubed. So now I have that that's going to be 4 over 75 pi, and then that's h cubed. So from here, if you know that the height and its rate of change is what the height is, or the depth at that moment, then you can actually just take the derivative with respect to h. Excuse me. So in this case, like yeah, if you did take the derivative, you would have that the derivative dv dt is equal to 4/25 pi h squared times dh dt. And then from there, yeah, you're just plugging in whatever h is and whatever dh dt is. Um, I mean, some of these are actually, to be honest, very easy, especially like if you have something like a cube. If you have something like a cube, then you know that you kind of know that you can actually just say that, well, the volume of a cube is just x squared. So in that case, you know that you can just, or not x squared, but x cubed. You know that you could just take the volume of that. So like volume equals x squared. Well, let's just say x cubed, like assuming that it was a cubed. Then you know that the related rates would be that dv dt equals to 3x squared times dx dt. mostly we deal with this like if you're thinking of like a heap of rubbish being compacted into a cube, knowing the rate of change for the edge. Like if you know that it's decreasing at a rate of 2 inches per second, then in that case, you can figure out what is the rate of change for the volume. Okay, so one thing that I'll leave you with is that you just need to look at different types of formulas, like for shapes, geometric shapes, like surface area, perimeter, Pythagorean theorems, all that kind of stuff. So if anything, just look at the Lone Star formula sheet that's in your course documents, and then try to see like if you can apply those to the different examples in the chapter for related rates.